All planets in our solar system move in the same direction around the Sun, from Mercury's close orbit to Neptune's distant path. None of them travel in the opposite direction. This shared movement is not random. It's evidence of how our solar system began, dating back 4.6 billion years when everything started as a spinning cloud of gas and dust. Tonight, we'll explore how the universe first began to spin. If you find this journey interesting, I'd appreciate a like or subscribe. Your support helps keep this content alive and reminds me to continue creating. Get ready as we start. Most planets in our solar system travels counterclockwise around the Sun when you look down from above the Sun's North Pole. This is one of the clearest patterns in astronomy and reveals much about our past. Why do 8 different worlds spread across billions of kilometers all move in the same direction? It seems like they're following an invisible rule from before they existed. This isn't coincidence. It's a frozen memory from when our solar system formed. About 4.6 billion years ago, before Earth existed, a huge cloud of molecules drifted through the Milky Way's spiral arms. The cloud contained mostly hydrogen and helium, with small amounts of heavier elements like carbon, silicon, and oxygen. These heavier elements came from older stars that had already died. This cloud was enormous, more than 100 astronomical units wide and hundreds of times heavier than our Sun. Gravity made it collapse inward. Here's the important part. As it got smaller, it spun faster. This principle is called conservation of angular momentum, one of physics' most basic laws. When figure skaters pull their arms in, they spin faster. The same thing happens in space. As the gas cloud shrank, any small initial spin became stronger. The whole cloud began spinning like a slow space hurricane. NASA's solar nebula theory explains this clearly. As the cloud collapsed, it spun faster and flattened into a disk. Within a few million years, the huge cloud became a flat, rotating sheet of gas and dust called a protoplanetary disk. Most of its material got pulled toward the forming Sun. At the disk center, the Sun ignited and nuclear fusion began. The remaining materials started clumping together. Tiny grains collided and stuck, forming pebbles, then kilometer-sized planetesimals. Collisions happened frequently and violently, but throughout it all, one direction dominated, the direction the disk was spinning. That spin created what we call the ecliptic plane, the invisible flat sheet cutting through the solar system. This explains why Mercury, Venus, Earth, Mars, Jupiter, Saturn, Uranus, and Neptune all orbit within a few degrees of each other. Their paths differ slightly and their speeds vary. Mercury circles the Sun in 88 days, while Neptune takes 165 years. Yet all move counterclockwise, sharing the same inherited motion. Astronomers have seen this pattern elsewhere. The Atacama Large Millimeter Array has photographed young stars wrapped in dusty disks, showing the exact same formation process. The Gaia mission also tracks newborn stars, confirming that disk-shaped systems are common outcomes of stellar birth. So why counterclockwise? Because the original solar nebula spun that way. The Sun itself rotates counterclockwise, completing one rotation roughly every 25 Earth days at its equator. Angular momentum can shift between objects but cannot disappear. The planets simply carried forward the motion of their parent cloud. In the beginning, it wasn't peaceful. The early solar system was full of impacts, collisions, and radiation. Still, through every shock and merger, that single spin continued. It was the universe's way of keeping order through motion. Modern simulations confirm this. When a molecular cloud collapses under gravity, angular momentum aligns along one axis, forcing the material into a flat spinning disk. Without this alignment, there would be no stable orbits, no flat solar system, and no planets as we know them. As Neil deGrasse Tyson said, "We're part of a universe that wants to spin. From galaxies to atoms, motion is its natural state." You can see this inheritance across the solar system. Saturn's rings move in the same direction as Saturn's orbit. The asteroid belt between Mars and Jupiter flows with the same current. Even the icy worlds of the Kuiper Belt follow this motion billions of kilometers away. When NASA's New Horizons passed Pluto in 2015, it confirmed that even at the solar system's edge, counterclockwise motion still holds. This shared direction is one of the most important clues to our origin. It shows the solar system isn't a random collection of worlds, but a single outcome of physics in motion. Every orbit we see, every rotation, every year that passes on Earth continues that first spin. The angular momentum Earth inherited controls its rotation, orbit, and even climate stability. Without that original direction, life as we know it might never have found balance. The same cosmic motion that shaped the sun's disk also created the conditions that made us possible. So tonight, as you imagine planets gliding silently around the sun, remember they're all following a rhythm older than the sun itself. What keeps that rhythm steady after billions of years? What force prevents the solar system from falling into chaos? The answer lies in the invisible plane that connects every orbit, the secret of why the solar system is flat. When we look at the solar system from above, it seems impossibly organized. Almost every planet from Mercury to Neptune moves within the same thin sheet of space. But why is everything so flat in a universe that began in chaos? Why did a cloud once wide and shapeless compress into a disk thinner than paper compared to its width? That question takes us deep into the physics of motion, pressure, and gravity, the quiet forces that shaped our cosmic home's geometry. At the dawn of the solar system, 4.6 billion years ago, the sun was still young, glowing faintly in a cocoon of dust and gas. Around it swirled a rotating cloud called the protoplanetary disk, roughly 200 astronomical units across, but only a fraction of that in thickness. This thinness wasn't accidental. It was a natural result of physics at work. Gravity pulling inward, centrifugal force pushing outward, and collisions canceling vertical motion. In the earliest stage before the disk flattened, material moved in all directions. Atoms and dust grains traveled upward, downward, and sideways, a turbulent soup of motion. But each collision between particles released energy. Vertical motions, those moving above or below the forming plane, lost momentum faster than motions around the center. Gradually, what remained was rotation around a single axis. As NASA's Jet Propulsion Laboratory explains, when particles collide within a spinning cloud, they begin orbiting in the same plane, creating a flattened disk. This process, called collisional damping, acted like friction in a vast cosmic centrifuge. Imagine spinning honey on a plate. The faster it rotates, the flatter it becomes. The same principle shaped our solar system. Gravity pulled gas inward, but conservation of angular momentum forced it outward along the edges. The balance between these forces produced a rotating disk with a stable ecliptic plane, the reference sheet where almost every planet now travels. The Atacama Large Millimeter Array has captured this process happening around other stars. In 2014, it imaged HL Tauri, a star only 1 million years old, surrounded by a disk of dust clearly divided into bright rings and dark gaps. Those gaps are where planets are already forming, embedded in a perfectly flat plane of orbiting material. NASA called the image a snapshot of our solar system's past. The most direct evidence ever seen that flattening isn't unique to our sun. It's the rule, not the exception. The reason this flattening is so universal lies in angular momentum distribution. When the cloud that birthed the sun began collapsing, tiny imbalances of rotation defined the shape of everything that followed. Gravity gathered mass toward the center, but not perfectly symmetrically. Every particle's motion had a slight sideways component. As they collided, those sideways components reinforced each other, aligning around the axis of greatest spin. Vertical movement was canceled out, leaving a single dominant direction of rotation. ESA researchers studying protoplanetary disks have described this precisely. According to their 2022 report, energy loss in the vertical direction leads to disk settling in less than 1 million years. That's incredibly fast. On cosmic timescales, the solar system became flat almost immediately after it began to spin. But flattening wasn't smooth. Within that thin disk, turbulence still raged. Regions of higher density pulled material inward while the sun's radiation pushed lighter particles outward. The balance between those forces created ripples, spiral arms of gas that twisted through the disk like slow-motion storms. Supercomputers at NASA's Ames Research Center simulate these flows today, using equations to model how the disk's pressure gradients evolved. They find that turbulence gradually gave way to smooth, ordered rotation, locking the structure into a thin, resilient sheet. Even now, evidence of that flattening surrounds us. All major planets orbit within just a few degrees of the ecliptic. Mercury sits 7 degrees above, Earth at 0 degrees, Mars only 1.8 degrees. The consistency is astonishing for a system born from chaos. If the solar system were the size of a dinner plate, the thickness of the planetary plane would be thinner than a single sheet of paper. That's how flat it is. The flattening also explains why the sun's equator and planetary orbits are closely aligned. Both inherited their motion from the same collapsing cloud. The sun's equator is tilted only about 7.25 degrees relative to the ecliptic plane, small but measurable. That subtle tilt likely came from later gravitational tugs by Jupiter and Saturn, not from the original formation. One of the most insightful observations about this structure came from Carl Sagan, who said, "The solar system is a flat disk because collisions made it so. The flattening is a record of billions of gentle impacts." It's easy to forget how violent those early years were. Thousands of objects crashing, merging, shattering. Yet out of that, symmetry emerged. The thinness of our cosmic plane is the fingerprint of all those collisions quietly canceling out the chaos. This isn't just a visual coincidence. That flatness defines how light travels through our neighborhood. The band of zodiacal light, that faint glow you sometimes see before sunrise, is sunlight reflecting off dust that still orbits within the same plane. Even the paths of most asteroids, comets, and moons align close to that disk, showing the gravitational framework remains intact. NASA's Lucy and Psyche missions were planned specifically within that plane because nearly all stable orbits exist there. The James Webb Space Telescope has deepened our understanding of this geometry. In 2023, its MIRI instrument imaged the star Beta Pictoris, showing an extended razor-thin debris disk viewed almost edge-on. It looked eerily familiar, a young solar system in formation, perfectly flat, glowing in infrared light. Scientists studying it noted temperature gradients indicating planet formation inside the disk. It was as though we were looking back in time at our own beginning. The idea of flatness may sound abstract, but it's essential for stability. A disk structure ensures that gravitational forces between planets remain balanced. If orbits were tilted at random angles, planets would constantly disturb each other, leading to collisions or ejections. The ecliptic plane keeps everything in check, like a tensioned surface where motion stays predictable. Even minor inclinations, Mercury's 7 degrees, Pluto's 17 degree, show how deviations increase instability over long timescales. And yet, this near-perfect flatness hides small irregularities that tell us more. The asteroid belt is slightly thicker than the planetary plane because its particles interact less cohesively. Comets from the distant Oort cloud fall in from random directions, proving that beyond the disk, space quickly becomes three-dimensional again. The solar system's flatness, then, is not universal, it's local. It exists because of the shared angular momentum of our parent cloud, not as a property of all space. NASA often describes this formation as the flattening of chaos into order. But unlike poetic metaphors, the mechanism is purely mechanical. Energy lost through collisions, gravity shaping equilibrium, and angular momentum defining motion. No external force designed it. Physics simply preferred the flat configuration because it was most stable. In other words, flatness is the natural resting shape of rotating matter in space. If we could watch time in fast motion, we would see billions of particles colliding, slowing, and aligning until random motions disappear and only the orbit remains. That's the quiet miracle hidden inside every solar system ever observed. From chaos to symmetry, from vertical to circular, all because of laws of motion that never forget. Now, astronomers continue studying new systems forming today. The TESS and JWST missions together have confirmed hundreds of young exoplanet systems showing the same disk geometry, proving our solar system's formation wasn't special but typical. We're seeing the same physics. The same flattening happens across the galaxy. If all solar systems begin flat, what happens as they age? Do gravitational interactions slowly warp their disks, tilting worlds out of alignment? Or do unseen forces, dark matter, passing stars, nudge them in ways we haven't yet measured? The solar system's slight tilt hints that something once disturbed us, and tracing that disturbance may tell us what else shared space with our sun long ago. At first glance, the solar system looks perfectly flat. All the planets seem to glide in one delicate layer around the sun, following the same invisible path. But if we measure precisely, that illusion breaks. Mercury's orbit tilts by 7 degrees. Mars only 1.8 degrees. Pluto, though now classified as a dwarf planet, leans an astonishing 17 degrees above and below the ecliptic. The solar system isn't a perfectly flat record. It's slightly warped, a cosmic sheet with subtle wrinkles carved by time, gravity, and ancient violence. So why aren't all orbits perfectly aligned? To answer that, we must step back to the solar system's chaotic youth. In those first 100 million years, planets were still colliding, migrating, and trading gravitational blows. Each impact, each near miss, nudged orbits slightly up or down, shifting the angles that remain to this day. NASA describes this era as a cosmic shooting gallery where countless planetesimals, some hundreds of kilometers wide, smashed together to build the worlds we know. These collisions didn't destroy the system's flatness, but they disturbed its perfection. Mercury, for instance, orbits the Sun at a tilt of about 7 degrees. That deviation likely dates back to early gravitational encounters with Venus and Jupiter, which periodically pull Mercury out of alignment. Because Mercury is so close to the Sun, Even a small force creates large effects. ESA's Bepi-Colombo mission is currently measuring that tilt with extreme precision, tracking Mercury's path to within meters. Its goal is to test general relativity by observing how the Sun's gravity warps Mercury's orbit over time. Further out, Mars tilts just 1.8 degrees, almost perfectly aligned, but not quite. Its orbital plane gently oscillates like a slow wave in a pond. This motion, called orbital precession, is caused by gravitational tugs from Jupiter and the residual mass of the asteroid belt. Every 2 million years, Mars's orbit shifts slightly, then settles again. The result is a stable but living geometry, always changing yet never chaotic. And then there's Pluto. Its 17 degrees inclination seems extreme compared to the others. But Pluto's orbit is locked in a resonance with Neptune. Every time Pluto completes 2 orbits, Neptune completes 3. This precise gravitational relationship prevents collisions even though their orbits cross. NASA's New Horizons mission confirmed in 2015 that Pluto's tilt and elongated path result from early interactions, possibly caused by Neptune migrating outward billions of years ago. The whole outer solar system bears trace of that migration, a fossil record written in orbital inclinations. To visualize what happens, imagine a flat pond covered in floating leaves. Each leaf represents a planet gliding smoothly at first. Then a pebble, a passing mass, drops into the water, sending ripples outward. Those ripples lift some leaves higher and lower others. The pond remains mostly flat, but no leaf sits perfectly level again. That's what Jupiter and Saturn have done for billions of years, their enormous gravity constantly sculpting the solar system's geometry. Jupiter, in particular, is the main architect of these inclinations. With a mass 318 times that of Earth, its gravitational field dominates. Every smaller world feels its pull. When their orbital frequencies align, a condition called orbital resonance, energy is exchanged, shifting each planet's tilt slightly. It's a quiet but relentless influence, invisible yet measurable. NASA's Juno spacecraft, orbiting Jupiter since 2016, continues to refine our understanding of how its gravity disturbs nearby space. According to the Solar System Dynamics Group at NASA's Jet Propulsion Laboratory, Jupiter's orbit oscillates by about 0.3 degrees every 70,000 years. Even such tiny wobbles can send ripples through the inner planets. Earth's orbital plane shifts by roughly 2.4 degrees over 100,000 year cycles, one of the drivers behind ice ages. So even the ground beneath our feet moves in response to distant gravitational music. The Laplace-Lagrange theory, first developed in the 18th century and refined with modern supercomputers, explains this mathematically. It shows that every planet's inclination oscillates within predictable limits governed by the mass and distance of its neighbors. The result is dynamic balance, not perfect alignment, but long-term harmony. ESA's Gaia mission has used this principle to study extrasolar systems, confirming that similar oscillations appear in other planetary families. In 2022, researchers at the Max Planck Institute used N-body simulations to recreate our solar system's evolution. They found that even small asymmetries in the original protoplanetary disk, perhaps a region of denser gas or a nearby passing star, could explain the initial tilts. Over billions of years, gravitational interactions among the planets amplified or dampened those angles, producing the pattern we see today. The takeaway is clear: perfect flatness is temporary. Gravity never stops sculpting. There's a quiet beauty in this imperfection. Each orbital tilt records an ancient event, a collision, a migration, or a gravitational encounter that once disturbed the balance. As NASA's Planetary Science Division put it, every deviation tells a story written in motion. Mercury's 7 degrees, Mars's 1.8 degrees, Pluto's 17 degree. They're not errors, but signatures of history. And despite those differences, the solar system remains astonishingly stable. The same phenomenon appears in other systems. Kepler and TESS have found hundreds of exoplanet families where most planets orbit within a few degrees of one another, but not perfectly. In some, like Kepler 56, the inner planets orbit at a steep 45 degrees angle relative to the star's equator, likely caused by a hidden giant planet pulling from afar. Such observations confirm that orbital inclination is a universal consequence of gravitational evolution, not a flaw unique to our system. So the solar system is both ordered and restless. Its architecture endures but never freezes. Each planet sways slightly in its orbit, tracing slow oscillations that repeat over millions of years. To the human eye, everything seems still. But if we could watch across geological time, we'd see the entire solar system breathing, expanding, contracting, tilting, yet always returning to balance. Carl Sagan once said, "The motions of the planets are a symphony, not a static diagram." And that is precisely what orbital inclination reveals, not disorder, but movement within order. The harmony of the solar system isn't born from stillness. It's born from the physics that allows variation without collapse. Now scientists are looking even deeper, using JWST and ALMA to study how inclination develops before planets even form. Observations of PDS 70, a young star 370 light-years away, show a warped disk divided into two planes, one inner, one outer, with a difference of nearly 30 degrees. Two giant planets, PDS 70b and 70c, are carving those layers apart as they orbit. It's a live view of how inclinations are born, gravity sculpting geometry in real time. What we see there is a mirror of what once happened here. If gravitational interactions can shape orbits so subtly, what happens over even longer scales, billions of years into the future? Will Jupiter's slow pull eventually push Earth out of its gentle plane? Will the solar system's flatness warp beyond recognition? Computer models suggest that while inclinations will oscillate, the system will remain stable for at least another 5 billion years, until the Sun itself begins to expand. So when we look up and see planets tracing similar paths across the sky, remember they're aligned not by perfection but by balance. Each orbit holds a memory of past disturbances, echoes of forces that still whisper through space. And deep beneath that quiet motion lies a question scientists are only beginning to explore. If gravitational interactions can tilt entire worlds, could they also shift the very center of the solar system itself? If you could rise above the Sun's North Pole and look down, you would see something remarkable. Every planet, Mercury, Venus, Earth, Mars, Jupiter, Saturn, Uranus, Neptune, all circle the Sun in the same direction, counterclockwise. The same pattern appears in their moons, in most asteroids, even in the Sun's own rotation. But why that direction? Why not clockwise? Somewhere in the deep past, the universe made a choice, or rather, physics did. About 4.6 billion years ago, long before Earth cooled or life began, the solar system was nothing more than a rotating cloud of gas and dust, the solar nebula. This nebula wasn't stationary. It spun slowly at first, then faster as gravity pulled it inward. And as it collapsed, it flattened into a disk, carrying with it a conserved direction of motion. That direction, fixed in the earliest rotation, became the template for every orbit that followed. Every grain of dust, every forming planetesimal, every future world, all moved counterclockwise, inheriting the momentum of their birth cloud. This is conservation of angular momentum, one of physics' most universal principles. It states that once rotation begins in a closed system, the direction and quantity of that spin remain constant unless acted upon by an external force. NASA explains it simply: the planets orbit counterclockwise because the cloud that formed the solar system spun that way, and nothing has stopped it. It's the same law that makes an ice skater spin faster when they pull in their arms or a collapsing star whirl into a neutron star after a supernova. Motion preserves memory. The sun itself testifies to this origin. It rotates counterclockwise when viewed from the north, completing a spin roughly every 25 days at its equator and 35 days at its poles. This uneven rate, called differential rotation, was first measured in the 17th century by Galileo using sunspots as markers. Later, NASA's Solar Dynamics Observatory confirmed it with high-resolution imaging, revealing plasma flows locked to that same ancient direction. The sun and its planets are bound not only by gravity but by shared angular heritage. Astronomers once wondered if this counterclockwise orientation was unique. Then telescopes like ALMA and JWST began observing other young stars. The answer was clear. Nearly every observed protoplanetary disk also rotates in a single direction, though from another vantage point it might appear clockwise. Direction, it turns out, is relative. What we call counterclockwise is simply the perspective from the north side of the solar system, defined by the orientation of Earth's magnetic poles. If we looked from the south, the entire system would appear to turn the opposite way. Still, the consistency is real and the physics universal. The first detailed model of this process was developed in the mid-20th century by Swedish astronomer Hannes Alfvén, who introduced the concept of magnetohydrodynamics, the study of plasma flows in magnetic fields. He proposed that the rotating solar nebula's magnetic forces helped align the gas into a coherent spin, transmitting angular momentum from the inner to the outer regions. Later missions like NASA's Parker Solar Probe confirmed that the sun's magnetic field indeed rotates with the same counterclockwise pattern, extending billions of kilometers outward in the solar wind. Even the interplanetary magnetic field carries that twist, a vast spiral known as the Parker Spiral, discovered in 1958. So when we talk about planetary motion, we're not describing independent objects. We're describing a single rotating system. The planets are like beads on a spinning wheel, each following the same curve traced by the sun's rotation and the disk that gave it birth. That's why the orbits remain in sync even after billions of years. And though gravitational interactions may slightly alter a planet's eccentricity or inclination, the overall direction remains fixed. One of the most striking confirmations of this shared direction came from the Voyager missions. As Voyager 1 and 2 crossed the orbits of the outer planets in the late 20th century, their instruments measured the orientation of the solar wind and magnetic field. Both probes found the same counterclockwise signature, perfectly matching the sun's rotation. Even at distances beyond 150 astronomical units, far outside Neptune's orbit, that primordial direction still dominates space. The Gaia mission adds another layer to this story. By mapping the motion of over 1 billion stars in the Milky Way, Gaia reveals that our sun is part of a larger galactic rotation. The Milky Way itself spins, and our solar cloud inherited part of that motion when it formed. In essence, our counterclockwise system is a small echo of the galaxy's own spin, embedded in a hierarchy of rotations that stretches across the cosmos. Carl Sagan once said, We are the legacy of motion, not of stillness. That legacy is literally written into the direction of our orbit. Some scientists have explored whether random external forces could have reversed that motion. For example, if a massive nearby star had passed too close during the solar system's formation, its gravity might have torqued the disk in the opposite direction. But simulations show that such a reversal would have destabilized the early sun and likely prevented planet formation altogether. The counterclockwise spin, therefore, wasn't chosen, it was preserved because it worked. Systems that form with coherent angular momentum are more likely to survive. Yet there are exceptions that make this rule even more fascinating. Venus spins in the opposite direction of its orbit, what astronomers call retrograde rotation. Uranus, meanwhile, is tilted nearly sideways, rotating almost perpendicular to its orbit. But even these rebels still orbit the sun counterclockwise, obeying the system's inherited motion. Most likely, both planets experienced giant impacts early in their history that flipped their axes without altering their orbital direction. This is a powerful reminder that while rotation can change, orbit remembers. In 2021, JWST's early science targets included disks around young stars such as TW Hydra and AS209. Their images showed gas swirling counterclockwise, just like our solar system, with planet-forming rings aligned in the same way. The more we observe, the clearer the pattern becomes. Nature prefers rotation. As physicist Brian Cox said, "Angular momentum is the heartbeat of the universe. From spinning galaxies to orbiting electrons, motion repeats itself across every scale." Still, one question lingers. What set that first spin in motion? Was it turbulence inside the Milky Way's spiral arms? A collision of clouds billions of years ago? Or something even larger, a universal bias in the way matter collapses under gravity? Astronomers studying galactic statistics have found no preferred global direction. Half of star systems rotate one way, half the other. Our solar system's counterclockwise orientation, then, is just one of countless possibilities, a coin flip in cosmic symmetry. Yet within that randomness, something profound remains: coherence. From the smallest dust grain to the orbit of Neptune, every motion still remembers that initial alignment. Over billions of years, through collisions, migrations, and gravitational waves, the solar system has never reversed. It keeps turning quietly, persistently, in the same counterclockwise rhythm first set at its birth. And that rhythm continues far beyond the planets. The Kuiper Belt objects, the scattered disk, and even interstellar visitors like Oumuamua carry traces of similar motion, as if still obeying an ancient rule. The solar system doesn't just spin, it remembers. But if every planet orbits in the same direction, how did two of them, Venus and Uranus, end up rotating the opposite way? What kind of impact could turn an entire world upside down yet leave its orbit untouched? Among all the planets that orbit the Sun, two refuse to spin the right way. Venus turns backward. Uranus rolls sideways. Every other planet spins in the same counterclockwise direction as its orbit. Yet these two worlds defy that cosmic rule. Why? What happened in the early solar system that could flip an entire planet on its axis without tearing it apart? To answer that, we have to return to a time when everything was still forming, when planetary collisions were not rare accidents but ordinary events. Roughly 4.5 billion years ago, the solar system was a crowded arena of half-formed worlds. Dozens of planetary embryos, rocky bodies hundreds to thousands of kilometers wide, orbited the young sun. They collided, merged, and scattered, shaping the planets we see today. NASA's Goddard Institute describes it as a period of violent accretion, where impacts decided the destiny of each world's rotation. Venus, nearly the same size as Earth, likely suffered one or more colossal impacts that reversed its spin. Today, it rotates clockwise or retrograde, completing one slow turn every 243 Earth days. That means its day is longer than its year. It takes only 225 Earth days for Venus to orbit the Sun. In other words, the Sun rises in the west and sets in the east, a world turned upside down. But the story of how it happened is complex. One leading theory, supported by data from NASA's Magellan and ESA's Venus Express, suggests that Venus's thick atmosphere, 90 times denser than Earth's, may have slowed and reversed its spin through tidal interactions. As sunlight heated one side more than the other, the dense air created torque against the planet's surface, gradually altering its rotation over millions of years. Another possibility is more dramatic. A single massive collision with a body nearly as large as Earth could have flipped Venus's axis outright. Computer models by the Southwest Research Institute show that such a strike could reverse a planet's spin while leaving its orbit intact. Both scenarios fit the observations, and both reveal just how fragile and dynamic early planetary motion really was. Uranus, on the other hand, is a case unlike any other. It rotates almost completely on its side, its axis tilted by 97.8 degrees. To visualize it, imagine a spinning ball knocked over so far that it rolls along its orbit instead of twirling upright. Its poles point nearly toward the Sun, taking turns bathing in sunlight and darkness for 42 years at a time. It is the strangest rotation in the solar system and one of the most studied. The leading hypothesis is that Uranus experienced a giant impact early in its history. Simulations by Durham University in 2018 show that a collision with a body 1 to 3 times the mass of Earth could have tilted Uranus without destroying its icy mantle. The computer models even predict that debris from such an event could form a temporary ring system, which might explain Uranus's faint, narrow rings today. As NASA put it, Uranus was likely knocked sideways by a cataclysmic impact billions of years ago, changing its axis forever. Yet despite those violent histories, both Venus and Uranus still orbit the Sun in the same counterclockwise direction as every other planet. Their rotations were altered, but their orbital paths stayed stable. This distinction is crucial. A planet's spin, its rotation around its own axis, can change through collisions or tidal effects. But its orbit, its path around the Sun, is governed by angular momentum shared across the entire solar system. The solar system's collective motion is too vast and too stable for one planet to reverse its course. In essence, Venus and Uranus are outliers in rotation but loyal followers in orbit. Their defiance highlights a deeper truth. Rotation is personal, but revolution is inherited, the memory of the original nebula's spin. The counterclockwise flow established 4.6 billion years ago remains locked into every orbit, unchanged by the passing of time. NASA's Voyager 2 flyby of Uranus in 1986 revealed more clues. Its magnetic field is not only tilted like its axis but also offset from the planet's center by almost 60%. That misalignment means Uranus's magnetic poles sweep through space like a wobbling flashlight beam. The result: auroras that wander unpredictably, a magnetosphere that flips with the seasons, and a rotation that behaves unlike any other planet. In 2022, the James Webb Space Telescope confirmed faint heat signatures in Uranus's atmosphere, consistent with that tilted energy flow. More proof that its sideways rotation continues to affect its weather even today. Venus, meanwhile, continues to puzzle scientists. ESA's Venus Express and Japan's Akatsuki orbiter have observed slow variations in its rotation rate, changes of up to 20 minutes per day over time. These fluctuations are likely caused by exchanges of momentum between its dense atmosphere and solid body. In other words, Venus's winds, moving at more than 360 kilometers per hour, literally push the planet beneath them. It's the most extreme case of atmospheric coupling in the solar system. Both planets challenge what we consider normal. They show that while angular momentum shapes the broad pattern of the solar system, local conditions, impacts, internal dynamics, and atmospheric effects can bend that pattern in remarkable ways. Carl Sagan once remarked, "Every world has its own biography written in its motion. Venus's backward turn and Uranus's sideways roll are simply two unusual chapters in that cosmic autobiography." The idea that a single impact could change a planet's fate isn't theoretical. Earth itself bears scars of such collisions. Most scientists agree that our moon formed when a Mars-sized body, Theia, struck Earth about 4.5 billion years ago. That collision altered Earth's rotation rate and axial tilt, creating the 24-hour day and the 23.5 degrees tilt that gives us seasons. If Earth's spin could be reshaped once, so could Venus's and Uranus's. This shared violence connects all planets. The calm orbits we see today are built on ancient impacts, gravitational battles, and recovered balance. Every tilted axis, every reverse spin carries the memory of a time when the solar system was still deciding its shape. And even now, those memories aren't frozen. Planets continue to shift, albeit slowly, under the influence of tidal forces and internal mass redistribution. So what would happen if a large asteroid hit Earth today? Could it tilt us like Uranus or reverse our spin like Venus? Current models suggest no. Earth's angular momentum and mass distribution are too stable for a reversal, though a massive enough impact could shift our day length by seconds or our tilt by degrees. Thankfully, such collisions are extremely rare in the current era. Still, these two planets, Venus and Uranus, remind us that the solar system is not static. It evolves, sometimes dramatically, and that even within an ordered system, exceptions reveal the true range of what physics allows. As Neil deGrasse Tyson said, "The universe is under no obligation to make sense to you. Retrograde rotation is the solar system's quiet way of proving that." So tonight, as we imagine the planets spinning in their slow ancient rhythm, remember that two of them dance out of step, backward, sideways, and yet never fall out of orbit. Their strange rotations are not mistakes but evidence of a universe that remembers every impact, every motion, every turn. And if collisions could tilt entire planets, what else might those ancient impacts have left behind, hidden deep inside their cores, waiting to be found? If the planets all orbit the sun in one unified direction, do their moons obey the same law, or do they carry their own chaotic memories of creation? At first glance, the answer seems simple. Almost every major moon in our solar system moves in the same direction as its planet orbits the sun. Prograde motion, aligned with the great counterclockwise current of the solar system. But one moon defies that pattern entirely. Neptune's moon Triton moves backward, circling in the opposite direction of its planet's rotation. And in that reversal lies one of the most dramatic stories in planetary science, a captured world that may have rewritten Neptune's history. When we study the moons of the giant planets, we find consistent architecture. Jupiter's Galilean moons, Io, Europa, Ganymede, and Callisto, all orbit prograde, locked in elegant resonance. each of them formed from the same circumplanetary disk of gas and dust that surrounded Jupiter as it grew. Like a miniature solar system, they inherited Jupiter's spin direction, orbiting counterclockwise when viewed from above the Sun's north pole. The same is true for Saturn, whose more than 80 moons, including Titan and Enceladus, all follow the same general rotation. Even Uranus, tilted almost 98 degrees, hosts moons that orbit in the same plane as its equator sideways, but still consistent with its own spin. These systems reveal a simple rule: moons that form with their planets share their rotation. It's a product of angular momentum, the same principle that shaped the planets themselves. When a gas giant grows, its gravity captures material from the solar nebula into a mini-disk. Collisions within that disk cancel random motion, flattening it and creating a local ecliptic plane around the planet. Small clumps condense, merge, and stabilize into moons. And because everything in that local system moves the same way, those moons end up orbiting prograde. NASA's Galileo and Cassini missions provided direct evidence for this process. Cassini's detailed mapping of Saturn's rings and moons showed that prograde satellites like Titan formed within a narrow zone of material rotating in harmony with the planet. Galileo's long-term observation of Jupiter's moons revealed that their orbital planes are almost perfectly aligned with Jupiter's equator, a clear fingerprint of formation in place. But Triton breaks that symmetry. Orbiting Neptune at a distance of about 355,000 kilometers, it travels clockwise, retrograde, against Neptune's own rotation. It is the only large moon in the solar system to do so. Its backward path is more than a curiosity. It's a mystery that puzzled scientists for decades. How could such a massive object, nearly as large as Pluto, end up orbiting in the wrong direction? The key lies in its origin. Unlike Jupiter's or Saturn's moons, Triton didn't form around Neptune. It came from elsewhere, the Kuiper Belt, a vast region beyond Neptune filled with icy worlds. Sometime billions of years ago, Triton was likely part of a binary system, two objects orbiting each other like Pluto and Charon do today. When this pair passed near Neptune, the planet's immense gravity tore them apart. One object was ejected into space. The other, Triton, was captured, pulled into orbit in reverse. Computer simulations from NASA's Jet Propulsion Laboratory and the University of Arizona show how this capture could have happened. For a stable capture, Neptune must have had a thick atmosphere of gas at the time, allowing drag forces to slow Triton down. Without that friction, it would have simply slingshot away. The energy exchange between Neptune and Triton was enormous, enough to heat Triton's interior and possibly melt its surface ice, producing the cryovolcanic features we see today. Voyager 2, which flew past Neptune in 1989, revealed the full strangeness of Triton. Its surface is smooth, young, and streaked with nitrogen geysers erupting up to 8 kilometers high. Its temperature is one of the lowest ever measured in the solar system, just 38 Kelvin, barely above absolute zero. And it moves backward, as if forever resisting the direction of everything around it. NASA's report from the mission summarized it simply: Triton is the coldest, strangest, and most unexpected world we have seen. This capture likely had catastrophic effects on Neptune's original moon system. Before Triton arrived, Neptune may have had several large moons like Jupiter or Saturn. When Triton was captured, its highly elliptical orbit would have destabilized the smaller satellites, scattering or destroying them. Over millions of years, tidal forces circularized Triton's orbit, pulling it inward to its current distance. Today it moves smoothly, but its presence carries the echo of that chaos. Scientists now believe that Triton's retrograde orbit is slowly decaying. Tidal friction between Neptune and Triton is causing the Moon to spiral inward at a rate of about 1 centimeter per year. In roughly 3.5 billion years, it may cross Neptune's Roche limit, the distance where tidal forces overcome its own gravity and disintegrate into a new ring system. If that happens, Neptune will temporarily resemble Saturn, with bright icy rings made from Triton's remains. Not all irregular moons are as dramatic as Triton, but many share similar origins. Jupiter and Saturn both host small retrograde moons, captured asteroids drawn in from beyond the main disk. Jupiter's moon Himalaya and Saturn's Phoebe both orbit opposite to their planet's spin. They are remnants of early solar debris, cosmic refugees trapped by giant gravity. These moons confirm a broader pattern. Regular moons form locally, irregular ones are captured. The James Webb Space Telescope has recently observed similar structures forming around young exoplanets. In 2023, JWST's NIRCam instrument imaged the disk around PDS 70c, a Jupiter-like exoplanet 370 light-years away. It showed a bright circumplanetary disk, the birthplace of future moons. Scientists noted that its orientation matched the planet's orbit, confirming that the laws of angular momentum repeat everywhere. But they also saw clumps and asymmetries, suggesting that capture events like Triton's may occur in other systems too. In this quiet order of orbits and directions, retrograde moons remind us that gravity doesn't erase history. It records it. Every backward orbit marks a moment of capture, a lost world folded into a new one. Triton's reversed motion is not disobedience. It's inheritance. It carries the signature of the solar system's violent youth, still circling in defiance yet perfectly balanced by physics. As Carl Sagan once said, "Every world has a story, and every motion is a memory of how it came to be." So do moons follow the same rule as planets? Most do, but a few, like Triton, Phoebe, or Nereid, whisper that not all motion begins where it ends. Some worlds are born twice, once in their home system, and once when gravity claims them anew. And that leads to a deeper question. If planets can capture moons, could stars capture planets too? Could some worlds orbiting distant suns, even rogue planets drifting between galaxies, be cosmic orphans adopted by new stars long after birth? For billions of years, the planets have moved together in harmony, counterclockwise, following the ancient rotation of the solar nebula. But scattered among them are a few wanderers that refuse to follow the flow. A handful of asteroids, less than 1 in 10,000, travel backward around the Sun. They orbit in reverse, weaving against the current of every planet and most moons. Why do they move the wrong way? And how can such motion even remain stable in a system ruled by order and gravity? According to NASA's Center for Near-Earth Object Studies, only about 0.01% of all known asteroids follow retrograde orbits. That means out of more than 1 million cataloged asteroids, only a few hundred defy the standard direction. They are cosmic exceptions, fragments of history that record gravitational chaos rather than cosmic harmony. Most of them were not born this way. They were thrown off course, scattered, or even captured long after the solar system's formation. To understand how that happens, imagine space as a vast gravitational ocean. Each planet creates waves, invisible currents of gravity that can push, pull, and redirect anything that comes close. When a small asteroid passes near a giant like Jupiter or Saturn, those currents can flip its orbit completely, reversing the direction of its motion. This phenomenon is called gravitational scattering, and it is one of the most powerful mechanisms in orbital mechanics. It shows that even within the order of planetary motion, chaos quietly endures. One of the most famous retrograde asteroids is 2015 BZ509, discovered by the Pan-STARRS Observatory in Hawaii. It orbits the Sun in the opposite direction of Jupiter and every other planet. Yet somehow it shares Jupiter's orbital period. That means it moves retrograde in resonance with Jupiter, completing one full orbit for every orbit Jupiter makes, but traveling the other way. It's like two runners on the same track, circling in opposite directions, passing each other at nearly 100,000 kilometers per hour, yet never colliding. This unlikely dance has continued for at least 1 million years. How is that possible? NASA's Jet Propulsion Laboratory describes it as a stable gravitational cohabitation maintained by precise orbital resonance. Because of the geometry of its orbit, 2015 BZ509 always meets Jupiter at safe distances. Their gravitational influences cancel over time, keeping both in balance. ESA researchers have modeled this configuration using N-body simulations and found that it could remain stable for hundreds of millions of years. In 2018, scientists at the Côte d'Azur Observatory proposed something even more extraordinary. 2015 BZ509 may not be native to our solar system at all. Its reverse orbit suggests it could have been captured from another star's planetary disk about 4.5 billion years ago. If true, it would make it the first known interstellar immigrant permanently residing in our solar system. Dr. Fathi Namouni, who led the study, said, "The only way to keep such an orbit stable for billions of years is if it started that way." That statement challenges our entire understanding of planetary history, that even in our own backyard, there may be remnants of other suns. Retrograde asteroids like BZ509 aren't alone. NASA's Minor Planet Center lists several others, including 343158, 2009 HC82, and 20461 Dioretsa, whose name literally spells asteroid backward. These bodies have elongated, inclined orbits that cross those of Jupiter and Saturn, showing how gravity's long reach can sculpt paths that seem impossible yet remain predictable. Each orbit is a compromise, a balance between chaos and control. The concept of retrograde motion isn't new. Astronomers have observed apparent backward motion in the sky for centuries, the illusion created when Earth overtakes outer planets in its orbit. But the retrograde asteroids are not optical illusions. They truly move in reverse around the Sun. This distinction, subtle but profound, marks the difference between perspective and physics. To maintain such reversed paths without crashing into prograde planets, these objects often occupy highly inclined orbits, some tilted more than 150 degrees relative to the ecliptic. That inclination acts as a safety margin, keeping them far above or below the plane where most planets travel. Still, their stability is fragile. Even minor perturbations from Jupiter's gravity or the Yarkovsky effect, a tiny push from uneven thermal radiation, can alter their paths dramatically over millions of years. The NEOWISE mission, which surveys near-Earth objects in infrared, has detected several small retrograde asteroids that occasionally cross Earth's orbital zone. Although they pose no current threat, their trajectories offer insights into how gravitational interactions can redirect ancient debris into new regions. Some may have started in the outer solar system, perhaps in the Oort cloud, before being scattered inward by passing stars or the influence of the giant planets. Others might have originated from disrupted moons or captured comets. One intriguing discovery from Gaia's second data release was the identification of hundreds of high-inclination asteroids in the main belt, objects that may represent transitional cases between prograde and retrograde motion. Researchers call them dynamical intermediates, asteroids that have been twisted by repeated resonances until their inclination flips completely. This gradual transformation shows how orbits evolve continuously, not suddenly under gravitational stress. Retrograde asteroids also help scientists test the limits of orbital mechanics. When a small object moves opposite the Sun's general motion, it experiences relative velocities far higher than normal. Collisions between prograde and retrograde bodies therefore carry extreme energy, sometimes enough to pulverize both objects into dust. This mechanism may help explain why regions like the asteroid belt and Kuiper belt contain so much fine debris. NASA's Lucy mission, launched in 2021, is exploring Jupiter's Trojan asteroids, which share the planet's orbit but cluster in two large groups, one ahead and one behind. Although all Trojans move prograde, Lucy's extended study will help model how gravitational resonances can occasionally flip orbits, offering clues about how retrograde asteroids like BZ509 arise. The data Lucy returns will refine our understanding of how small bodies migrate and sometimes rebel within the Sun's gravitational field. The James Webb Space Telescope, though designed for deep space, has also observed asteroids, measuring their heat and spin. Its precision photometry helps determine the composition of retrograde objects, revealing whether they match main belt asteroids or interstellar materials. Early data suggests that some of these reverse-moving bodies are unusually dark and carbon-rich, closer in chemistry to comets or Kuiper belt objects than to inner belt rock. That supports the capture hypothesis. Many retrograde asteroids may have been imported from the outer solar system. Despite their rarity, these objects play a vital role in cosmic stability. They act like gravitational pressure valves, absorbing excess energy from planetary interactions. Without them, resonances between Jupiter, Saturn, and the asteroid belt could grow chaotic faster. Their presence ensures that the solar system's complex choreography, its blend of order and unpredictability, continues undisturbed. Carl Sagan once observed, "The universe is not perfect order nor perfect chaos, but the endless conversation between the two. Retrograde asteroids are that conversation made visible. They are the exceptions that prove the rule, the reminders that motion is never static, only balanced." So the next time we imagine the solar system turning silently in one grand direction, remember, somewhere out there, a few stones are moving against the tide, not lost, but in orbit, held steady by the same laws that govern every planet, every moon, every ring. And if a tiny rock can defy the motion of an entire system and still endure for millions of years, what else might be hidden in those backward paths? Fragments of other systems? Or echoes of collisions that once reshaped the solar system itself? Every so often, a glowing visitor appears in the night sky, a comet, bright tail unfurling, racing across the stars. But unlike planets, comets don't obey the quiet symmetry of the solar system. They fall in from every direction, tilt at every angle, and sometimes even move backward around the sun. Some swing by once and are gone forever. Others return after tens of thousands of years. They are the solar system's wild cards, the restless fragments of its frozen frontier. Where do they come from? The answer begins far beyond the planets, beyond even Pluto and the Kuiper belt, in a region so distant that sunlight there is only a faint memory. This is the Oort cloud, a vast spherical shell of icy bodies surrounding the solar system, extending up to 100,000 astronomical units from the Sun, nearly 1.5 light-years away. First proposed in 1950 by Dutch astronomer Jan Oort, it explains why comets appear from every direction rather than from a single plane. Unlike the orderly disk that formed the planets, the Oort cloud is three-dimensional, shaped by billions of years of gravitational scattering. NASA describes it as a distant reservoir of frozen objects, the leftovers of planetary formation. Most comets were once part of the inner solar system, ejected outward by the gravity of Jupiter and Saturn during the solar system's youth. Those that went far enough never returned. Instead, they settled into orbits so large and so random that together they formed a sphere, a halo of ancient debris encasing everything. Some were nudged into motion again by passing stars, galactic tides, or molecular clouds, falling back toward the sun after millions of years in darkness. When they re-enter, we see them as long-period comets. One of the most famous is Comet Hale-Bopp, discovered in 1995. Its orbit stretches more than 250 astronomical units at its farthest point, and it won't return for another 2,500 years. When it last visited, it shone brighter than any star, visible even in daylight. Hale-Bopp's extreme path, inclined by 89 degrees, almost perpendicular to the ecliptic plane, demonstrates how chaotic the Oort cloud's geometry truly is. By contrast, short-period comets like Halley's Comet originate closer in from the Kuiper Belt, a flattened region beyond Neptune. But even Halley's path isn't typical. It too travels retrograde, orbiting the Sun backward once every 76 years. Astronomers believe Halley was once a long-period comet from the Oort cloud that was captured into a shorter, stable orbit by Jupiter's gravity. Its reverse direction, preserved ever since, makes it a bridge between the structured inner solar system and the chaotic outer realm. ESA's Rosetta mission offered the first up-close look at a comet's surface. 67P/Churyumov-Gerasimenko, discovered in 1969. This comet follows a much shorter orbit of just 6.5 years, looping between Jupiter and the Sun. Rosetta's instruments revealed its strange peanut-shaped nucleus, active jets of dust and vapor, and complex organic molecules, materials unchanged since the dawn of the solar system. When scientists compared the isotopic composition of water on 67P with Earth's oceans, they found subtle differences, suggesting that Earth's water may not have come from such comets after all. Even in their chaos, comets carry the chemical fingerprints of the solar system's first moments. The diversity of cometary motion, from Halley's retrograde path to Hale-Bopp's steep tilt, reveals how the solar system interacts with its galactic environment. Every few million years, a nearby star passes close enough to the Sun to disturb the Oort cloud. Even a small gravitational nudge can dislodge thousands of comets, sending them spiraling inward. It's a reminder that the solar system is not isolated. It lives inside a galaxy that continually stirs its edges. In 2015, the Gaia mission mapped the positions and motions of more than 1 billion stars. Among them, astronomers identified several that have passed near the Oort cloud in the past few million years. The closest known, Scholz's star, came within just 0.8 light-years about 70,000 years ago, close enough to perturb Oort cloud objects. It may have triggered some of the long-period comets that later entered the inner solar system. Future encounters will do the same. Gravity keeps the cycle alive. Disturbance, return, and evaporation. The James Webb Space Telescope has recently begun observing comets in unprecedented detail. In 2023, JWST detected carbon dioxide, methane, and complex hydrocarbons in Comet 238P/Reid. confirming that even small comets hold prebiotic materials. Its data also revealed faint traces of crystalline silicates, indicating that material from the warm inner solar system was once transported outward and frozen in the Oort cloud. That means comets are time capsules, each one a sealed record of the solar system's chemical exchange across billions of years. NASA's Deep Impact and Epoxy missions showed just how unpredictable these visitors can be. When Deep Impact deliberately crashed a probe into Comet Tempel 1 in 2005, the explosion revealed water ice, clays, and carbon compounds beneath the surface. What surprised scientists most wasn't the composition but the density. Comets aren't solid, they're fragile aggregates, more porous than snow. That fragility explains their sudden fragmentation near the sun, as if the heat simply unravels them back into dust and vapor. The orbital tilt of comets can be extreme, often more than 100 degrees, making them nearly perpendicular to the planetary plane. Some even swing past the sun from above or below, their paths slicing through the solar system like blades of light. This randomness is a signature of their birthplace. In the Oort cloud, there is no north or south, no preferred rotation. Objects are distributed evenly in all directions, a frozen sphere bound only by the sun's faint gravity. When one of these distant bodies begins its inward fall, its orbit can take millions of years to complete. A single journey from the edge of the Oort cloud to the inner solar system can span geological epochs. And when it finally approaches the sun, the radiation ignites its frozen gases, creating the glowing tail we see from Earth. A brief flare before another long silence. Comets, in that sense, are less like travelers and more like returning messengers, fragments of the solar system reporting from its distant borders. Carl Sagan once described comets as the deep frozen relics of creation. Every time one appears, we witness material unchanged since the solar system's birth. Its orbit may be chaotic, its path unpredictable, but its chemistry is ancient. To watch a comet is to look directly at time, not flowing but circling. Astronomers now suspect that the Oort cloud may extend beyond the sun's gravitational boundary, merging subtly into the interstellar medium. If so, some of its comets might already drift between stars, carrying traces of our solar system to others, and perhaps bringing theirs here. That idea gained weight after the detection of Oumuamua in 2017 and Comet 2I/Borisov in 2019. Both confirmed as interstellar visitors. Borisov, in particular, resembled a typical solar system comet in structure and chemistry, hinting that Oort cloud-like formations may be universal. So comets, though chaotic, obey a deeper pattern. They connect systems. Their extreme orbits, tilted and reversed, are not accidents but echoes of a time when gravity ruled without symmetry. They remind us that the solar system's edges are not boundaries but bridges, linking our sun to the stars beyond. And if the Oort cloud can send its icy fragments inward, could it also send larger ones? Rogue planets or ancient bodies still drifting unseen in the dark? For centuries, astronomers assumed that all planets everywhere must orbit their stars in the same direction that their stars spin. It seemed obvious. Angular momentum, after all, is conserved. Every world should follow the spin of the first cloud that gave it birth. But in 2009, that quiet certainty broke. Scientists found a planet that didn't just tilt or wobble. It moved the wrong way around its star. Its name was WASP-17b, and its orbit rewrote the rule book of planetary motion. Discovered by the Wide-Angle Search for Planets, WASP project in collaboration with the European Southern Observatory, WASP 17b is a gas giant about 1,000 light-years from Earth in the constellation Scorpius. It is what astronomers call a hot Jupiter, a giant planet larger than Jupiter but orbiting extremely close to its star, completing one revolution every 3.7 Earth days. But what makes WASP 17b extraordinary is its direction. It moves retrograde, orbiting in the opposite direction to its star's rotation. That single observation shook one of astronomy's most fundamental assumptions, that planetary systems form with everything spinning the same way. To confirm that, astronomers used a precise tool called the Rossiter-McLaughlin effect. As WASP 17b passed in front of its star, it blocked different regions of the star's rotating surface. This caused tiny shifts in the star's spectral lines, the fingerprints of its motion. From those shifts, researchers could tell that the planet's orbital path was almost perfectly opposite the star's spin. It wasn't a misalignment of a few degrees, it was a full reversal 150 degrees out of sync. This was the first time we had seen a planet orbiting backwards, said David Anderson, a member of the Discovery team. It told us that nature can create systems far stranger than we ever imagined. How does such a world come to exist? The answer lies in the violent youth of planetary systems. When stars form, they are surrounded by disks of gas and dust where planets begin to take shape. Normally, everything in that disk rotates in one direction. But if the system experiences a major disturbance, such as a close encounter with another star or the gravitational tug of massive neighboring planets, the orbits can tilt, twist, or even flip entirely. This process is called gravitational perturbation, and it can transform a stable, aligned orbit into a retrograde one. NASA simulations show that large planets forming in the outer regions of a system can migrate inward over time, their orbits decaying due to interactions with the disk or with other planets. In rare cases, a close gravitational encounter, sometimes just one pass between two giant worlds, can flip a planet's orbit 180 degrees while leaving it gravitationally bound to its star. In the case of WASP 17b, scientists believe that such an encounter occurred early in its history, possibly involving a massive unseen companion planet. After the risky encounter, tidal forces from the star circularized the orbit but preserved the reverse direction. The result is a world locked in a stable but rebellious path, a planet forever moving against the rotation of its own sun. And it's not alone. Since 2009, astronomers have discovered several more retrograde planets. HAT-P7b, Kepler 17b, and KL-29b all show significant misalignments, some exceeding 100 degrees, hinting that orbital flips may be more common than we once thought. ESA's Cheops and NASA's test missions continue to refine these measurements, finding that up to 30% of known hot Jupiters have misaligned or retrograde orbits. That means the early lives of planetary systems may be far more turbulent than ours was. These findings also help explain why hot Jupiters, massive planets orbiting close to their stars, are often alone. If their inward migration was triggered by chaotic gravitational events, those same events could have ejected or destroyed smaller neighboring worlds. As Dr. Joshua Wynne from MIT put it, the universe doesn't build solar systems the way we would build models on a table. In 2023, the James Webb Space Telescope observed WASP 17b directly, measuring its atmospheric composition. The results were stunning. JWST detected water vapor, sodium, and hints of titanium oxide, molecules that affect the planet's temperature and clouds. The planet is 1.9 times Jupiter's diameter but only about half its mass, meaning it's extraordinarily low density, a puffed-up gas giant. Its retrograde orbit likely contributes to this expansion. Tidal forces stretch its atmosphere as it battles the star's gravity in a reversed path. WASP-17b's discovery also changed how scientists think about planetary alignment itself. For decades, we assumed systems form in flat, neatly aligned disks like our solar system. But now evidence shows that many systems are tilted, warped, or chaotic. Some stars even spin on axes that differ wildly from the plane of their planets' orbits. The Kepler mission revealed systems with planets orbiting at multiple inclinations, forming stacked layers instead of single planes. It seems our solar system's near-perfect alignment is not the norm but the exception. Astronomers are now mapping these tilts using astroseismology, studying stellar oscillations to determine how a star is oriented. When compared with exoplanet orbits, the data reveals surprising diversity. Some systems are polar, where planets orbit over the star's poles rather than around its equator. Others are retrograde, moving completely opposite. These findings imply that the calm architecture of our solar system may be a rare outcome of gentle evolution, not a universal pattern. Still, even in reversal, WASP-17b obeys the same fundamental laws of motion. This backward path is perfectly stable. Its orbit is predictable to the second. It doesn't break physics. It simply shows physics in a different configuration. As Neil deGrasse Tyson once said, "The universe is under no obligation to make sense to you." And in WASP-17b's reversed orbit, we see that truth unfold, order written in the language of apparent chaos. In 2022, astronomers discovered another extraordinary system, K2-290b and K2-290c. Two planets orbiting a binary star at nearly opposite inclinations. The system's outer companion star likely distorted the inner disk during formation, tilting it drastically. This demonstrates that even the gravitational presence of a nearby star can twist a planetary system's geometry into something counterintuitive. Retrograde orbits, then, are not errors of creation. They're signatures of stellar interaction, traces of stellar neighborhoods that once collided. ESA's Gaia mission is currently tracking the motions of millions of stars, allowing scientists to trace possible past encounters between young systems. Already, the data shows that close passes between stars in dense stellar nurseries are common, especially within the first 10 million years of their lives. Each encounter can disturb disks, scatter planets, and create misaligned or retrograde configurations that persist for billions of years. WASP-17b, therefore, may not be unique, just one of the most dramatic survivors of that early cosmic turbulence. To imagine it, picture a system where the star spins one way but its planet rushes the other. A permanent gravitational tension, as if two massive bodies were locked in a cosmic tug-of-war that never ends. Each orbit stretches the planet's atmosphere, stirs its clouds, and warms its dayside to more than 1,700 Kelvin. Yet the orbit endures, stable, repeating, precise. Even in reversal, the math holds. So yes, entire planets can orbit backward. But those rare orbits don't contradict the laws of physics. They reveal the depth of their reach. Gravity doesn't prefer symmetry, prefers consistency. And even in the strangest configurations, it keeps the universe balanced. But that raises one final question. If planets can orbit backward, could stars themselves ever reverse their spin or move against their galactic flow? Every planet spins the same way. Almost every moon follows that rhythm. And yet, when you look closer, small deviations appear. Tilts, reversals, captured wanderers, orbits that seem slightly off. It looks chaotic, but it isn't. Hidden inside that chaos is a pattern, one that tells us how order itself was born. Roughly 4.6 billion years ago, there was no sun, no planets, no structured geometry, only a cloud of molecular gas and dust, cold and drifting in one arm of the Milky Way. Then gravity began to pull it inward. As the cloud collapsed, it started to rotate, a slow spin that, according to the law of conservation of angular momentum, accelerated as the nebula contracted. From that single motion came every orbit, every spin, every rhythm we know. NASA describes this moment as the solar system's ignition, when a diffuse cloud of elements from earlier stars condensed into the structure we now inhabit. The rotation wasn't perfect. Turbulence, magnetic fields, and random collisions sculpted eddies within the disk. Yet even within that turbulence, one direction dominated. The nebula flattened into a protoplanetary disk with the young sun forming at its center. Around it, rings of gas and dust began to coalesce, giving birth to the planets. This simple, natural process explains why most planets orbit counterclockwise and lie roughly in the same plane. But it also leaves space for exceptions. The solar system didn't form quietly. It was shaped by impact, migration, and instability. The early NICE model, developed by scientists at the Observatory of the Côte d'Azur, describes how the giant planets, Jupiter, Saturn, Uranus, and Neptune, once migrated through the disk. Their shifting orbits scattered smaller bodies in every direction, some inward to form the asteroid belt, others outward into the Oort cloud. In those encounters, the seeds of retrograde motion and tilted orbits were planted. When Jupiter and Saturn entered a 2:1 resonance, completing orbits in a synchronized pattern, their combined gravity disrupted everything around them. Planetesimals were ejected, captured, or slammed into forming worlds. This chaotic ballet lasted only a few 100 million years, but it set the foundation for long-term order. The solar system's architecture stabilized only after surviving its own internal storm. ESA's Gaia and JWST missions now show that this process, chaos birthing order, is not unique. When Gaia mapped thousands of young stellar systems, astronomers noticed that most protoplanetary disks were slightly tilted, warped, or misaligned with their stars. And yet, over time, gravitational settling smooths those distortions. Planets may begin in disorder, but they end in rhythm. As one ESA scientist put it, alignment is not the starting point of the cosmos. It's the outcome of its evolution. Even within the solar system, the transition from chaos to order is written into its composition. Meteorites contain isotopic signatures, ratios of oxygen and magnesium, showing that material from different regions of the disk mixed during formation. That mixing required turbulence, shock waves, and energy. It was messy, but it produced uniform chemistry, the same building blocks found across Earth, Mars, and the asteroids. In 2022, samples from the OSIRIS-RX mission to asteroid Bennu confirmed this. The dust there shares the same elemental fingerprints as ancient meteorites, tracing back to the solar system's original disk. Even the sun itself holds this memory. Its equator spins faster than its poles, a relic of the nebula's uneven collapse. And yet its magnetic cycles remain consistent, flipping every 11 years, anchoring the solar system in predictable rhythm. This is how cosmic order emerges, not by eliminating irregularities, but by harmonizing them over time. Every retrograde orbit, every tilted axis, every captured moon is a fossil of a collision, a gravitational tug, or a close pass that the solar system survived. Together, they form a record of endurance. When scientists at NASA modeled the evolution of the solar system backward in time, they found that even small instabilities, like Jupiter's slight eccentricity, were essential for long-term balance. A perfectly symmetric system would be unstable. It would collapse or eject planets. In other words, the solar system is orderly not because it is perfect, but because it is imperfect in just the right ways. The study of extrasolar systems confirms this idea again and again. Some exoplanet systems, like TRAPPIST-1, show almost perfect alignment, 7 rocky planets orbiting in a compact flat plane, synchronized in orbital resonance. Others, like Kepler-56, are wildly tilted, 2 planets orbiting at 45 degrees, influenced by a distant giant companion. And yet both systems are stable. Nature builds many versions of order. When JWST imaged the young star HL Tauri, it revealed a disk already carved into concentric rings, planets forming within a few million years of the star's birth. Each ring aligned with the disk's plane, showing that even in infancy, rotation and gravity begin imposing structure on chaos. The ALMA array confirmed this in other systems. Even turbulent disks eventually flatten, guided by angular momentum. In the broader view, this principle extends far beyond planets. Galaxies too form from collapsing clouds. They spin, flatten, and settle into disks of stars, another layer of cosmic order emerging from chaos. The same law that shaped the solar system sculpts spiral arms and star clusters across the universe. Carl Sagan once said, "The cosmos is within us. We are made of star stuff." But it's also true that we are made of spinning star stuff, of dust shaped by rotation, gravity, and time. The solar orbiter has been studying the sun's polar regions, searching for the roots of its magnetic field. Those poles, where magnetic lines twist and reconnect, drive the 11-year solar cycle that governs space weather across the solar system. It's a living example of how systems stay balanced. Tension builds, releases, and restores order. That same dynamic chaos stabilizing into pattern is the foundation of every planetary system we've ever observed. The solar system's shared direction, then, is more than coincidence. It's evidence that the laws of physics always push toward structure, that gravity, magnetism, and momentum conspire to organize even the most turbulent beginnings. Retrograde orbits and tilted axes are not failures of that order. They are footprints of how it was achieved. When Voyager 1 looked back at Earth from 6.4 billion kilometers away, the spacecraft captured the pale blue, a single pixel suspended in sunlight. In that moment, the entire system, every orbit, every spin, every captured fragment, was contained within one faint beam of light. It was visible proof of cosmic order, fragile, complex, but complete. So what does all of this tell us about the origin of order? It tells us that order isn't a starting condition. It's an outcome, that the solar system, like every structure in the universe, was born in turbulence but shaped by rules that never break. And that from those rules, gravity, rotation, conservation, comes stability that can last billions of years. NASA scientists often summarize this beautifully. The solar system is not static. It breathes. It shifts. It endures. That endurance, the quiet persistence of pattern through chaos, is what defines cosmic order. And tonight, as we close this journey through the motion of worlds, remember that everything from the smallest moon to the largest orbit began as dust and drift, yet found rhythm. Our solar system is not perfect, but it is coherent. It is the lasting harmony of motion carved from the noise of creation. Every planet in our solar system moves in the same counterclockwise direction because they all inherited the spin of the original gas cloud that formed them 4.6 billion years ago. This shared motion is preserved through the law of conservation of angular momentum. The solar system is flat because collisions between particles in the spinning disk canceled out vertical motion, leaving only rotation around a single plane, the ecliptic. Not all orbits share the exact same plane because gravitational interactions, especially from Jupiter and Saturn, have slightly tilted each planet's path over billions of years. Ancient collisions and migrations also contributed to these small deviations. All planets orbit counterclockwise because that was the direction the original solar nebula spun. This direction was locked in at formation and has been preserved ever since. Venus and Uranus rotate backward or sideways due to massive impacts early in the solar system's history. However, their orbits around the Sun remain counterclockwise like all other planets. Most moons follow the same rule, orbiting in the same direction as their planet's rotation. But a few, like Neptune's Triton, orbit backward because they were captured from elsewhere rather than forming with their planet. A small number of asteroids orbit backward due to gravitational scattering by large planets like Jupiter. These rare objects represent less than 0.01% of known asteroids. Comets have extreme, often backward orbits because they come from the Oort cloud, a spherical shell of icy objects with no preferred direction. They were scattered there billions of years ago and now fall back toward the Sun from random angles. Yes, entire planets can orbit backward around their stars. WASP-17b was the first discovered in 2009. These retrograde exoplanets likely had their orbits flipped by gravitational encounters with other massive planets early in their system's history. All of this tells us that cosmic order emerges from chaos through the consistent application of physical laws. The solar system's patterns, its shared rotation, flat structure, and stable orbits, are not perfect designs but natural outcomes of gravity, collisions, and angular momentum working together over billions of years. The exceptions, retrograde rotations, tilted orbits, captured moons, are not mistakes. They are memories of the violent events that shaped our cosmic home. Order doesn't require perfection. It only requires balance. And in that balance, carved from ancient chaos and preserved through time, we find the lasting harmony of motion that defines our solar system, and indeed, the entire universe.